Dear students, today we are going to discuss about the Markonikov's rule and along with that the anti-Markonikov's rule. Before moving on to the Markonikov's rule, first of all I will tell you what carbocations are. Carbocation mean when you remove one hydrogen atom or R group from a hydrocarbon, then the one formed is a carbocation. So think there is a hydrocarbon like this, and I am going to remove a hydrogen atom from that. The product formed is R, C, R and H. This carbon is with a positive charge, so the product formed is carbocation. And there are three types of carbocations as primary carbocation, secondary carbocation and tertiary carbocation. Right? If there is only one R group attached to the carbon, then it is primary carbocation. When there are two R groups attached to the carbon atom, then it is a secondary carbocation. And when there are three R groups attached to the carbon atom, then it is a tertiary carbocation. Right? Okay. Now we will focus on to the stability of carbocations. So when we talk about the stability of carbocations, we should first know that carbon has an electronegativity value of 2.5. That means a higher electronegativity value, right? 2.5 is comparatively higher. So carbon likes to have a lower positive charge. So here R group is rich in electrons. So when carbon is attached to R groups, they donate electrons to the carbon atom. So here for the primary carbocation, there is one R group and it donates electrons to the carbon and its positivity is like this. And for the secondary carbocation, two R groups are donating electrons for it. So its positive charge is like this. And for tertiary carbocation, there are three R groups donating electrons to it. So its positive charge is like this. So carbon has a higher electronegativity value and it likes a lower positivity. So the more stable carbocation is tertiary carbocation, and when you compare primary and secondary carbocation is more stable. You should remember this point when you move on to Markonikov's rule. That is explained here. When alkyl groups are attached to positively charged carbon atom of the carbocation, stability of the carbocation increases. Reason for this is the release of electrons by alkyl groups mean R groups, through carbon-carbon bond towards positively charged carbon atom to which they are attached. This results in decreasing the positive charge on the carbon atom, thereby stabilizing the ion. So the stability of the carbocation varies as follows. So you can see the way of stability of the carbocation. So this is a tertiary carbocation, this is a secondary carbocation, and here is a primary carbocation. Then we will see what happens to an alkene when it is reacted with hydrogen halide. So this is applicable to alkynes also, but I am explaining you through an alkene, right? So my alkene is this one and this is an asymmetric alkene. Why I am saying that it is asymmetric? When you divide this by the double bond, one carbon has two hydrogen and the other carbon has hydrogen and alkyl group. So that is asymmetric. And now I am going to add the hydrogen halide HBr for this one. There are two possible products. Let's see what are they. What are the possible products? Here in HBr, hydrogen can be gone to here and bromine can be gone to here, as well as bromine can be gone to here while hydrogen can go to here. Right? This product is mentioned here and this product is mentioned here. So now we are going to see the most stable one out of this using the carbocations. So let's see how to find the carbocation. We have to focus on to the carbon atom where bromine is attached. Right? This is the center. And here this is an R group. Here is a hydrogen atom and here is a hydrogen atom. This should be removed from the mind because this is a cation. Now two hydrogen and one R group. So what is this? This is a primary carbocation. So now remember this is primary carbocation. Let's focus on to the other one. This is the carbon where bromine is attached. So this is the central. And to this carbon, here one R group is attached and another R group is here. Here is a hydrogen atom. You should remove this from mind. So this is a carbocation with two R groups. So this is a secondary carbocation. So now you know that there are two possible products and one is primary and the next one is secondary. Out of primary and secondary, the most stable one is secondary carbocation. So we have to mention this as the most stable one. If you focus on to the most stable one, hydrogen has gone to the place where with more hydrogen and bromine has goes to the place where with less number of hydrogen, and this is what Markonikov has said. According to Markonikov's, when a protic acid means hydrogen halide, is added to an asymmetric alkene, hydrogen adds to the carbon atom bonded to higher number of hydrogen atoms. And in anti-Markonikov's, HBr adds in the opposite way to the Markonikov's rule. In Markonikov's rule, we know that hydrogen goes to the place where with more hydrogen. But in anti-Markonikov's rule, this happens in the opposite way. If we want to add hydrogen to the place where with less number of hydrogen and bromine to the place where with more hydrogen, then we have to do this reaction in a peroxide medium. That means we have to add RO, ROO, R, right? Just you should remember that this anti-Markonikov's rule is only working for HBr. HCl and HI are also two types of protic acids, but they do not follow the anti-Markonikov's rule even though we add ROOR. So here, if you directly add HBr for this will be your product. And if you add HBr in a peroxide medium, then this will be your product. Anti-Markonikov's rule. HBr adds in the opposite way to the Markonikov's rule when there are carbonic peroxides in reaction medium. Hydrogen adds to the carbon bonded to lower number of hydrogen atoms. Here L is missing. Lower number of hydrogen atoms. This is to be noted that direction of addition of HCl and HI is not changed in the presence of peroxide medium. This is to be highly noted.
Subscribe for more content.